Welcome to a lesson with Dr. Powell. Let's take a look at how we can take a matrix as a map, see how it splits, and how that helps us to write any vector at all in three space in R3 in terms of its projection onto the plane determined by these two vectors, the rows, and an orthogonal component to it. So if you have a plane here, and you have a vector coming off here, its projection onto the plane, and this vector right here. How can we find two such vectors? That's perpendicular or orthogonal right there. And we're going to do it completely with matrix multiplication and using using some nice facts about matrices in R. So first of all, A is a matrix going from R3, since there's three columns, to R2, since there's two rows. We're going to split this map with a map T. We're going to define T this way. A transpose multiplied by the inverse of AT. Now, why does this have an inverse? Well, for one thing, this is actually a map from R2 to R2. Imagine if you had something here, imagine you'd have this map right here. Okay, the result's going to be a 2 by 2, and actually it's going to be an invertible matrix completely when we do that. And due to the way that we can find areas of parallelograms or other things and some other results. But basically, if its rows are linearly independent, which means they actually create a two-dimensional area very nicely, then AAT will be invertible, so that'll be nice. So T is going to be a well-defined map here. And it's going to split this in which way? Well, let's see. If we take A times T, we'll do it here. A times T, regroup. Notice we're taking this is an inverse over here of this, and multiply together will just be the identity in R2, the identity matrix 1, 1, 0, 0, which is great. So A times T as a map, it's a matrix, but as a map, it's going to be the identity here. And that is so nice, because let's see what happens if we take the matrix A, and we'll just take any old vector V, and let's subtract TA of V, where this is multiplication by V here, and TA is actually, notice what it is. So we have T composed with A before it is a map right here onto R3. And from R3 to R3 itself is what we have when we have TA. And so we can take a vector and apply this splitting to it to come back here to kind of normalize it in some sense. It comes back here to V. And notice when you plug this into A, see what happens. We get AV, you get AT, but ATA, because we're putting an A before that. And notice what the AT is. AT is the identity. So that's like nothing. So it's like AV minus AV. Well, that's just the zero vector here in R3. So this is really a zero vector in R3. And what does that mean? Well, for one thing, that means that if we take A times this column, you're going to get 0, which means, okay, so you have a column vector multiplied here, and the different entries are just this dotted with that and this dotted with that. Well, wait a minute. If the dot product is 0, that means you have some kind of orthogonality that's perpendicular components. So this right here, V minus TAV, is actually the orthogonal component here in this triangle. And notice that that this expression right here is actually equal to V itself. You've taken V and you've split it up into orthogonal, plus TAV, okay, and that cancels out, so that should be normal. Now look at this. Notice that the last matrix you're multiplying by is AT. which means the column, which means your output is in the column space of AT. Column space of AT is just the row space over here of A. So, well, that's amazing because that means this is in the plane. So you've projected, so this vector is something orthogonal to the plane equal to something orthogonal to the plane plus something in the plane. Therefore, we've been able to decompose V successfully into an orthogonal component and to another component by using this kind of fun splitting map. In fact, it is true that any surjective map in this way with R modules or R vector spaces will have a splitting like this. And we've just shown how to define it exactly in this way. And because this is surjective, actually that ensures that this will have an inverse and we'll be able to proceed just like that. Kind of a fun idea that it can be split that way. Is it applicable for applications? Maybe there's other ways of doing it. However, in just plopping things in computations and running scripts and things like that, there are some nice things about this. For one, once you fix your plane, your two vectors, and you can quickly compute what T is, what the matrix T is. And then for the matrix T and the matrix A, and maybe you can compute what TA is. So you compute what TA is, and then it doesn't matter what vector you're talking about, you just put it into this, and you'll always get the orthogonal component and the projection quickly after you fixed your plane. So once you fix your plane, you have a very quick mechanism to get how vectors decompose with respect to it. So that is advantageous over other methods. It's always nice to be able to see things in more than one way. Thanks for watching.